excited to be here today. Thank you very much for the organizers of WiDS for this wonderful conference. And thank you for staying to hear me. I hope it makes it worth for you. So I'm Rachel Wities, and I'm going to talk about the challenges of the world of healthcare NLP. And spoiler, it's not just the doctor's handwriting that is complicated. A little bit about myself. I work as a data scientist in Microsoft Healthcare and Life Sciences team. And yes, Microsoft has a healthcare team here in Israel. And I'm also one of the co-founders of MET, together with Taliat Ron and Mila Orlovsky, who you met here today, and also Yelet Efrati, who is now in Finland. And an interesting story about MED. MEDS actually started a year ago right here in WiDS, in a round table of Taliat Ron, who eventually brought us together, all of us together, and started this community. So one lesson you can already take from my talk, maybe the most important one: keep in touch with everyone you met here today. Wonderful things can happen. And now back to medical text. Let's start with a question. On your last visit to the doctor, how much of the time did the doctor look at her screen instead of at you? Who says 10%? Who says about 30%? Who says about 50%? Who says more than 50%? Wow, okay, sad, but unfortunately true to reality. As of 2018, 50% of doctor-patient time was spent by the doctor on looking at the screen. And overall, including the time that the doctor isn't seeing patients, 2/3 of physician hours were spent on computers instead of on patients. And just a minute. Doctors don't like it, as you can see from the title. They see it as something that spends their time on something that is not necessary, and they would rather see patients. It also causes a high level of burnout. So let's see how we can help doctor. Most of this time is spent on reading and writing text and filling forms. And as we all know, as data scientists, there are many different AI applications to help with it, right? Starting from information extraction, text summarization, decision support, patient visualization, and so on. So in Microsoft, create Text Analytics for Healthcare, which is a building block that helps healthcare institutions and companies use medical free text in order to create all of these applications. And this is the pyramid of need. The doctor wants to save time. Healthcare institutions and companies want to create applications that help doctors save time. And we in Text Analytics for Health make the medical text more friendly for the healthcare institutions who want to help the doctors. And this is us, the Text Analytics team, Text Analytics for Health team in Microsoft. And those of you in NLP will understand that Sesame background. So this is what I'm going to talk about today. First of all, I'm going to talk about the challenges of utilizing free text medical records. Why is it hard? And why the healthcare institutions who want to create those applications need us. Then I'm going to present Text Analytics for Healthcare and explain how it helps utilize free text. And then I'm going to talk about a challenge that we had as the group developing Text Analytics for Healthcare when we wanted to turn it into a multilingual service. So let's start. Why is it hard to utilize free text medical records? So working with free text is always hard, as we all know, but there are some specific features in medical text that make it even harder. First of all, over 50% of the text in electronic healthcare records is duplicate. Why does it happen? We said before, doctors don't like to spend a lot of time on computers. So every time they need to write documentation or fill a form, they just copy-paste from a previous visit or a previous doctor. And this creates redundancy in the text. Another problem we have is a lot of underlying medical knowledge. Doctors write to other doctors. They assume some level of medical knowledge that our model doesn't necessarily have. And the third thing is what I like to call 50 shades of maybe. Doctors want to record all the findings and the possible findings they find. And this is why you will sometimes hear a lot of expressions like suggestive of, can't rule out, consistent with, and so on. Now, it's very important for us, as the people who create application based on this text, to take all of this into account, because we want to differentiate between a case when a doctor is almost completely certain about the finding and just needs a little test to confirm it, and a case when the doctor just writes something because it's the protocol, but the finding isn't actually there. And as in any other domain, we also have abbreviation, typos, synonyms, individual writing styles. You can see here there are a lot of ways to refer to one term. There are also, in languages that use transliteration, like in Hebrew, a lot of ways to write one term. And I told about the individual writing styles. So I was once sitting with a medical expert from the company, and we were looking at the radiology report, and the medical expert said, "Hey, I know the doctor who wrote the report." And I said, "How do you know? It's anonymized." So he said, "This patient suffers from atelectasis." And the doctor uses in Hebrew the word sircha. There's only one doctor in Israel who uses the word sircha to refer to atelectasis, so I know for sure he wrote this report. Okay, so we can see it's hard to normalize between the different medical records in reference even to the same specific term. So now I will show how our building block of text analytics for health can help the healthcare institutions work with free text. So this is the thing we do in text analytics for healthcare. We extract some knowledge out of this text. First of all, we do named entity recognition, which means we mark important medical entities, and we also write here what type of entity it is, diagnosis, symptom, or sign, and so on. The second thing we do, you can see here behind my back, that, for example, temperature is negative. So we extract the assertion level. Remember what I said about the 50 shades of maybe? So we actually have 5 different levels of certainty in order to be able to account for all these different levels of certainty in medical reports. The third thing we do is relation extractions. It's very important because some of the entities don't have any meaning, like 8 years, don't have any meaning when they're not connected to the thing they refer to. For example, here, ramipripil. And the final thing we do is entity linking. You can see here next to every term a little code from UMLS. It means that we linked it to a medical ontology. Why is it important? So first of all, you can see here on the top SOB, which is an abbreviation for shortness of breath. And at the bottom, you can see trouble breathing. And you can see that both of them were actually linked to the same term in UMLS. So it helps us normalize different ways to refer to the same finding. And another thing that entity linking gives us is this underlying medical knowledge I spoke about before. Inside every medical ontology, for every finding, you can also get a lot of other information about this finding that is not necessarily stated explicitly in the text. So these are all the ways in which text analytics for health can help healthcare institutions and companies who want to utilize medical text for applications. And this is just one example of a use case that utilizes text analytics for health. This is an application for nurses, so they don't need to actually carry the computer with them wherever they go in the hospital. They have this application on their smartphones, and they can dictate whatever they want. There's a speech-to-text algorithm that does a transcription. This is not us, this is Nuance. But then we come and we extract from this transcription all the important entities, and we know where to place them in the electronic health record. So we save the nurse a lot of time of copy-pasting from the transcription to the correct place in the clinical record. So this is just one use case. We work with a lot of companies and institutes around the globe. And now I'm going to talk about a challenge that we had when we wanted to turn this service into multilingual. If you lost me before, now it's a good time to come back because I'm starting something new. So as you can see here, as of now, our service is multilingual. We support 7 different languages, including Hebrew, which is very important to the Israeli ecosystem. But how did this happen? So when we started, we had a big problem, which a lot of you, I assume, also have in your domains. We had a very small amount of annotated data in languages that are not English. Now, generally in the medical domain, we have a very small amount of data because of privacy issue. Even less annotated data because it requires a lot of expertise to annotate our data, and even less data for non-English. So we used 2 different ways in order to overcome this problem. The first one is multilingual knowledge transfer, and I brought here this quote from Shakespeare to explain it. So in Romeo and Juliet, Juliet says, "That which we call a rose by any other name would smell as sweet." And what she means, if she was a data scientist, then she would say that knowledge transfers between languages. What I mean here is that if you know in English that an apple is a type of fruit, and then someone taught you that tapuach is an apple and pri is a fruit, then you wouldn't need him to explicitly tell you tapuach is a sug shel pri in order to understand that in Hebrew the same relation holds. You just have this knowledge from English and you transfer it to Hebrew. Okay, it sounds trivial, but this is how we work when we learn a new language. But this doesn't necessarily happen when we train a multilingual language model. Because a multilingual language model, even if we train one language model for a few languages, it would look separately at a Hebrew text and English text, and create a representation for tapuach, which has all the information from the Hebrew text, and for apple, which has all the information from the English text. And they wouldn't necessarily be able to learn from each other and get information and transfer information between them. So in this work we did, we used a model called XLM-K that was developed in Microsoft in a different team that actually enables our language model to do this cross-language transformation of data. And the way they do it is that part of the training is letting the model look at an article from Wikipedia, they mask one of the words, and they expect the model to understand or to predict to which of the other articles this word will lead. For example, here it needs to guess that the masked word apple, whether it needs to say whether it will lead to the article of Apple, the article of Apple the company, or just the general article of fruit. But this is not the catch, okay? The catch is here. They don't give it the article of Apple in English, they give it the article of Apple in, say, Arabic or Chinese or English. So what the model learns here is to understand that the word apple in this context is actually the same as the definition of apple in Arabic. And then, for example, Arabic, and then it can transfer knowledge from one language to another. So we use this XLM-K model. We first pre-trained it on a public dataset of non-annotated medical texts in different languages, and then we fine-tuned it on a very small internal dataset of annotated data. I'm talking here about less than 100 documents for each language. It's almost a few shot learning, okay? And with this, we were able to achieve results that were good enough for production level. You can see here behind me how it works beautifully in Hebrew and in other languages too. So this is one way we use to compensate for our lack of multilingual data. Another way we used is federated learning, just getting more non-annotated data using creative ways. So remember that I said before, it's hard to get medical data because of privacy issues. But what if we could train our algorithm on data from a healthcare institution without actually ever getting this data outside of the medical institution? So this is what happens in federated learning, and I'll explain how it happens. We take the general model and we copy it locally on all the different healthcare institutions. And then in each healthcare institution, the internal model learns from the data of this healthcare institution without exposing it to anyone. And then we update the weights of the general model using the deltas from the little local models. Okay, so this is how it generally works. And we wanted to check a little different case. We wanted to check a case when these are not just different institutions, but these are institutions each in different language. Okay, so this is federated learning on different languages. Why is it important? Why is it risky? Because the success of federated learning is very dependent of the distribution of the data between the different silos, between the different healthcare institutions. So we know that actually it still can work even if the hospitals are in different countries, if the hospitals treat different ages, for example, if it's a hospital for old people and another hospital for young people. But would it work if these are also other languages? Different languages have very different distribution of data between them. So for this, we did an experiment. We took multilingual data from public data sets, and one time we trained it like we would train it regularly, just the centralized model that gets all the data together. And the second time we pretended that we don't have direct access to this data, and we trained it using federated learning. And then we compared the two. Now I need to explain what we're measuring here. We measure the model perplexity. Model perplexity actually helps us understand how much the model understands our language. And the score here says how much the model is perplexed, how much it is surprised when it sees a new example. We don't want the model to be surprised. So here, lower is better. So you can see here that in federated learning and in centralized learning, we got the same perplexity, which means that we can use federated learning on multilingual languages. And now, following this successful proof of concept, we actually have a project with לאומית קופת חולים, where we get access like this with federated learning to millions of Hebrew medical records. And we improve our Hebrew, or the performance of our Hebrew model all the time thanks to that. So let's sum it up. Okay, we used multilingual knowledge transfer and federated learning in order to compensate for the lack of multilingual data. We were able to create our tool that helps take free text and make it into a structured data. And now healthcare institutions and companies can build different applications with it in order to help the doctor to see the patient. And this all for us, the patient who sits there on the top of the pyramid and just wants the doctor to be able to turn from her computer and see us. Thank you very much.